Hi, all of you. Good morning. Welcome to another lecture of nanoelectronics, the Shubnikov D-Haas effect and the quantum Hall effect. Myself, Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET Pyramid, leading the session. This is the topic in Module 5 of KTU syllabus. First, what is Shubnikov D-Haas effect? Actually, this effect is a periodic variation of the electrical resistivity of degenerate solids with 1 by H, where H is the strength of the static magnetic field. The periodic variations depends on the magnetic field orientation with respect to the direction of the crystal axis in the solid, and it is given by 2 pi He divided by Cs, where S is actually the maximum cross-sectional area of the Fermi surface. Okay, now this phenomenon is basically caused by changing the occupation of Landau levels in the vicinity of Fermi level in the plane perpendicular to the direction of magnetic field applied. We will see what is Landau levels. The electrons moving in a perpendicular magnetic field are forced onto circular orbits following the Lorentz force. That is, electrons moving in a perpendicular magnetic field are forced onto the circular orbits. They are forced to the circular orbits following the Lorentz force. They perform cyclotron motion with angular frequency omega c, or here we have represented it as omega. What is omega c actually? Omega c is equal to Eb by m, which is called the cyclotron frequency, where m is the electron mass, b is the magnetic field, and E is the charge of an electron. That is omega c is equal to Eb by small letter m. The available energy levels for the electrons are quantized. That is, the available energy levels for the electrons are quantized, and these quantized energies are known as Landau levels. In the previous slide, we saw the Landau levels, changing the occupation of Landau levels in the vicinity of Fermi energy will result in this formation of this phenomenon, and the quantized energies are known as Landau levels, and these are given by Ei. Okay, Ei is equal to I plus 1 by 2 into H omega c. You can write it as omega c with I is equal to 1, 2, 3, etc. The next type of effect is the quantum Hall effect. The phenomenon we have learned Hall effect. You know what is Hall effect. We have learned it in the solid state devices. The phenomenon of developing potential difference across the transverse sides of a current carrying conductor in a magnetic field is called Hall effect. Now what is quantum Hall effect? The same in the quantum phenomenon, or when you say it in quantum level. The quantum Hall effect is the quantum mechanical version of the Hall effect observed in 2D electron system subjected to low temperatures and a strong magnetic field in which hole conductance takes on the quantized values. Okay, that is sigma is equal to, we can say V E square by H, where H is the Planck's constant and E is the elementary charge. Sigma is given by, that is the conductivity may be given by V into E square by H. Okay. Now what is actually the quantum Hall effect? When the Hall effect is measured at low temperatures in a sample containing two-dimensional electron gas in which electrons are confined to move only within the plane, the Hall resistance is found to deviate from the classical behavior. From the basic behavior, there was a slight change in the behavior of the electrons when it was in a two-dimensional electron gas or a containing, that is when the Hall effect was measured at low temperatures in a sample containing two-dimensional electron gas, then it was found that the Hall effect, or sorry, the Hall resistance was found to deviate from the classical behavior. At sufficient high fields, a series of flat steps appear in the graph as shown, which is referred as the quantum Hall effect, or we can represent it by QHE. We can write it as QHE. Suppose in the if a question comes, what is QHE? Explain QHE. Then you have to write the quantum Hall effect. That is, we'll see the graph, then you will understand. This was in the normal case, a classical Hall effect, that is, it was a straight line when you consider a normal Hall effect with the magnetic field. That is a classical Hall effect. But in the case of a quantum Hall effect, we can see that there was some bends in the graph, and that is called this is actually called the quantum Hall effect. Now, the Hall resistance at positions of plateaus of steps is quantized to a few parts per billion actually, where h is a Planck's constant and I is an integer. RH is given by RH is equal to h by I e square. Capital RH is equal to small h divided by small I into e square. Okay, where h is the Planck's constant and I is an integer. Okay, where you can see in this graph there is a portion where you can represent it as 1, 2, etc. Such an effect was found to be, or consequently, since it was numbers, we call it as, consequently this effect is called as integer quantum Hall effect, since there was 1, 2, etc. Okay, this effect is definitely material independent, and it was also explained in terms of the Landau levels. Later, after 2 years, there were some more experiments in this field, and it was found that the integer quantum Hall effect, there was quantization could take place also in fractional levels. That is, here you can see 2 by 3, 3 by 5, or where I, which we represented earlier as 1, 2, etc., was changed to be 2 by 3, 3 by 5, 1 by 3, etc. In general, the I is given by I is equal to P by Q, where P and Q are integers, and this phenomenon was given the name fractional quantum Hall effect, or FQHE. That is the two types of quantum Hall effect, that is integer quantum Hall effect and fractional quantum Hall effect. That is, the Hall resistance is basically given by RH, capital R suffix h is equal to small letter h divided by I into e square, where I is given by 1, 2, 3, etc. in the case of integer quantum Hall effect, and I is equal to 2 by 3, 1 by 3, 3 by 5, etc. when it is in the case of a fractional quantum Hall effect. Now the applications, main applications was found to be in metrology. That is, the measurements in actual quantum Hall effect has allowed the determination of new physical standard for electrical resistance. That is, one of the most important application of QHE is in the field of metrology. And in 1998, a von Klitzing constant was found, which was Rk, that is resistance value. It is given by Rk is equal to h by e square, that is Planck's constant divided by e square. That is, that the value was found to be 25,812. Okay. Or you can say the measurements in the quantum Hall effect has allowed the determination of a practical standard of electrical resistance, which was found to be 25,812.8 ohms. Thank you for patient listening.